Hello everyone, welcome back. This is Dr. Rhonda Cofeld and this is the last part of our discussion on thermodynamics. And in this part, we're going to continue looking at the delta G zero. This time we're just going to calculate it using Hess's law, which we've already learned from chapter 9 and from figuring out delta H and delta S. So you already know how to do Hess's law. And that's the one where we have the reactions and we might reverse them and reverse the sign and things like that. Also, though, at the end of this, in the exciting finale, we're going to calculate delta G of the reaction, which notice doesn't have the little zero anymore, which means at non-standard conditions. Okay, and so we are going to have a little correction for that, and so we will look at that and have one more equation to learn. Okay. All right. So free energy of formation, we said the delta G zero of the reaction is the sum of all the products minus the reactants. We've already done this. Free energy of formation of pure elements is zero. Okay. So just like when we saw the delta H's, okay, the delta G zero of anything in its elemental form is also going to be 0. And so when we go to figure this out, we're going to, am I getting ahead of myself? Okay, yeah, so we've got methane. Let me get to where I am. All right, so this is example 18.8, and I was actually already looking at 18.9. All right, so calculate the delta G zero of the reaction from the standard free energies of formation of the delta G. Okay, so delta G has formation values as well, and so for this, I'm just looking at delta G, and so the delta G zero of the reaction from the delta G zero of formations is just going to be the products minus the reactants, and you use the formation. Okay, the formation form of this. All right, so I'm going to go ahead and write them down. I've got a negative 50.5 for my methane. Oxygen is 0. I've got a negative 394.4 for my CO2. I've got a negative 228.6 for my water, and I've got a positive 163.2 for the ozone. Notice that's O3, not O2. Okay, and so these are all going to be in kilojoules per mole, these values. Okay, because remember, when I do products minus reactants, I'm going to multiply how many moles times the kilojoule per mole, and that gets rid of it. All right, so my delta G zero of reaction is going to be products minus the reactants. All right, so I got a negative 394.4 plus, so that's 394.4 plus 2 times negative 228.6 plus 4 times my ozone value, which is a positive 163.2, and that's going to be minus negative 50.5 plus 0. All right, and so I'm going to put that in my calculator, and that's going to give me a negative 198.8 kilojoules minus a negative 50.5, so plus 50.5 kilojoules, because this is all G, and that's going to equal a negative 148.3 kilojoules. Okay, so this is the method of formations. So if you're given the method of formations, then you just have to do products minus reactants to find your delta G. Just like if you had delta H0 of formation, you do the same thing. So for all three of these things, you did it exactly the same way. And I gave you plenty of practice on this one at different temperatures and all that kind of good stuff. All right. So if a reaction, so just like before, I was trying to do Hess's law earlier, if you remember. So like before, when we saw the delta H, we can also look at the delta G values in a stepwise reaction, and it's still extensive. So if we reverse the reaction, we reverse the sign of the delta G value. If the amount is increased, we multiply the value by that. All right, and so hopefully you remember you did these Hess's laws before, and so you should remember this as well. All right, so I'm going to do it. Remember, what we're shooting for is to get 3 C's plus 4 H2s, giving us C3H8. I think we've done this before, but we didn't do it with the G's. We did it with the H's. Okay, so so if you recall, the first thing I want to do is I want everything that's going to be on the left-hand side to be on the left-hand side in each one of these reactions. So my carbon's good and my hydrogen's good. This one's going to have to reverse. So I already know I got to reverse that one. And then I'm going to have to multiply them by whatever number it takes to get them to have the same number of moles when I get done after I cancel out as my final overall reaction. Okay, so that's the overall reaction. And I'm calculating the delta G0 of the overall reaction. So I know I need 3 carbons. So I'm going to have to multiply my carbon one by 3. All right. And so that's going to give me 3 carbons, 3 oxygens, and 3 CO2s. And I'm going to have to multiply my delta G0 by 3. I need 4 H2s. I already have 2. So I'm going to have to multiply that by 2, which would give me 4, 2, and 4. And I'm going to have to multiply that number by 2. All right. Now, this top one, I have to reverse it. So I'm going to go ahead and reverse it. Because why am I reversing it? Because I have to have this as the product, and right now it's being written as the reactant. So I'm going to go ahead and I'm just going to rewrite this up here. 3 CO2, so I'm just flipping it, plus 4 H2Os gives me C3H8 plus 5 O2s. All right, now I only need one of these, so I don't have to multiply it by anything, but I just had to flip it. So when I flip it, that means that I have to reverse the sign, so it now becomes positive, but I'm multiplying it by a 1. So I already have the information to figure out what my delta G0 of the overall reaction is. But you go back and you check and make sure, you know, you've got 3 carbons, 4 hydrogens, and 1 C3H8. You've got 5 oxygens on this side, and 3 plus 2 is 5 oxygens on that side, right? Because we're not looking at this one anymore because I rewrote it. And then 4 waters over here. Let's see. 4 waters over here and 4 waters over there. So we're all good. I think I've got it. And 3 CO2s and 3 CO2s. All right, so now all I have to do is the math on the Hess's, on the delta G0s, and so I get a negative 1182.9, and these are all kilojoules, and no wait, Is that the right one? Let me make sure I'm not getting them mixed up. No, I am. Let me do this. I need to make sure I'm writing them in the same order so I don't confuse you. All right, so this first one is positive. It's times 1, so it's plus 207.4 kilojoules. And then the second one, the 394 one, is a negative 1182.9 kilojoules. And then the last one is 2 times the negative 457, so that's a negative 914.2 kilojoules. And so when I add all of those up together, that's 20, sorry. That would be a mistake right there. It's 2074. All right, gotta watch it all the time. So then my total is going to be a negative 23.1 kilojoules, and that's the overall. So it is going to be slightly exothermic, right? Slightly spontaneous. That's not negative 23.1. Not a huge. We've seen big numbers, right? It is spontaneous though at that temperature, whatever this temperature is. What is it? 25, right? Because that's standard conditions. So this is Hess's law, exactly the way we did it for the delta S and the delta H, but now we're doing it for the delta G. All right, so delta G equals delta G0 only when everything's in their standard states. The normal state temperature, the 1 atmosphere for all the gases, and 1 molar concentration for the liquids. And if it's not at those standard states, then we have to correct for it by using the normal delta G0 of the reaction plus R times T, okay, times the natural log of Q. That's our old buddy. We've seen Q before, haven't we? When we studied equilibrium, we saw Q a lot, and so it's rearing its ugly head again for us to figure it out. Hopefully you're going to remember how to do that, okay? So, and remember, at equilibrium, your delta G is 0, and your Q would equal K. Right? Yeah, it's coming back. Okay. All right. Your R is going to be what I call the energy form of the ideal gas law constant, which is 8.314 joules over mole K. And then your temperature must be in Kelvin. Okay. And so we're correcting for any changes that are outside the standard that we base our tables on, because if we get outside that, then the values are going to be different. All right. Okay. So our formula that we're going to be using is the delta G of the reaction. Notice no 0 is equal to the delta G0 of the reaction. I'm checking because I want to make sure that it's actually, yeah, okay. So many things you subtract. I just wanted to double check before I told you. Plus RT times the ln of Q. Okay, so delta G0 of the reaction plus RT times the natural log of Q. All right, so now we're going to calculate this under these conditions. Notice that we have normally at room temperature and at standard conditions, remember what that was? 1 atmosphere, okay? Then we would get a negative 71.2 kilojoules, and that is spontaneous, okay? That's a good spontaneous reaction. But our conditions, we have concentrations of 0.1, 0.1, and 2 atmospheres. And so the question is, is the reaction more or less spontaneous under these conditions than under standard conditions? This is standard conditions, and so we're going to run this calculation and we're going to see, is it more negative, which means it would be more spontaneous, or is it less negative and it would be less spontaneous? All right, so the first thing we have to know is what Q is. So Q, we're going to have to do the K, basically. So the partial pressure of the NO2, which is the product, and that's going to be squared, right, because there's two of them, divided by the partial pressure of NO squared times the partial pressure of O2. All right, and again, this is how we write them when they're gases, but if you write it the other way, like we do with the brackets and all that, not a problem, okay? Okay, and so then we're going to plug our numbers in. So 2 squared divided by 0.1 squared times 0.1. That's 0.1 cubed, isn't it? All right, and so when you put that in your calculator, and make sure you use parentheses around these guys when you are dividing by two things, okay? And you're going to get 4 times 10 to the third. 4 times 10 to the third as your Q. So I know Q. All right, it didn't change my temperature, so my temperature is 298. I know R, and then I know what the delta G0 is, right? So my delta G0 is a negative 71.2 kilojoules. And my, what was the other thing I needed to know besides temperature? Oh, R, which is 8.314 joules over mole K. All right, R and T and L and Q. Okay, and so, and then Q is this. So once I get all that figured out, then all I have to do is plug it into my formula. The delta G of the reaction is going to be equal to the delta G0 of the reaction plus RT natural log of Q equals. All right. Now, one thing I'm gonna look at is this is in joules and this is in kilojoules, and that would really mess me up, wouldn't it? So I'm going to convert that to the negative 71,200 joules from 71.2 kilojoules. Hopefully y'all can do that in your head by now. All right, so you got a negative 71,200 joules plus 8.314 joules over mole K times 298K, because it didn't say anything about being a different temperature, but I could have changed it, couldn't I? And I could put that in there. But since I'm comparing it to the standard condition, I want to leave everything else the same. And then times the natural log of my Q, which is 4 times 10 to the third. All right, so this is like my correction factor. Okay, it's my correction factor. So when I put that in my calculator, I'm going to get a negative 71,200 joules plus, and you got to be super careful. I'd do your natural log thing first and then multiply it by those two numbers. You should get 20,500 joules. So that's going to equal a negative 50,700 joules, or a negative 50.7 kilojoules. Now, when I do that, I look at, and it asks me, is it more spontaneous or less spontaneous? So this is the delta G at these concentrations, and the delta G with the 1 atmosphere concentrations was a negative 71.2 kilojoules. So which one is more negative? that one is. Negative 71 is more negative than a negative 50.7. So this is going to be less spontaneous. And that just means it's going to require more energy in the grand scheme of things. Okay, it would take less energy at at the 1 molar concentrations than it would at these lower concentrations. Okay, so it's still spontaneous, but it's less spontaneous than under standard conditions. There's your practice. If you're interested, you should get a negative 129 kilojoules for that one. I'm giving you that one because that one's a little crazy. And that is it for our thermodynamics discussions. Dr. Rhonda Kofelt, thank you for staying with me, and I'm out.